Thank you very much, all of you. My name is Mauro Coco. I'm part of Julius team. This talk will be about how to build a MapReduce generic pipeline by using our RuleDSL. So to summarize briefly how this talk is going to be organized, first we will do an introduction on the MapReduce programming model. Then we will jump onto our Julius web server and we will start building just from scratch a generic pipeline. And we will use a word count example to guide ourselves on how to build it. Then we will show also some other examples on how to reuse this generic pipeline to tackle another problems. In the end, I will be showing how easy it is to make distribution based on the same code we will develop together. So let's first talk about MapReduce problem. This is a programming model that was first introduced by two researchers on Google on 2004. This was discussed under a paper called MapReduce: Simplified Data Processing on Large Clusters. So I don't know if you are all familiar with this, but I will try to explain it as best as I can. So this is a strong a programming model strongly oriented to parallel and distributed execution, which is particularly good to tackle large amount of data and computing. And it is built to be simple, fast, scalable, and fault resistant. The first implementation of this was introduced to Hadoop, so you can find the implementation of MapReduce on these tools as well. So what's the idea of the MapReduce programming model? So the idea is that you can split your data source into multiple batches, and these multiple batches can be sent to several workers. So the idea is that when you apply a MapReduce, you're usually thinking on a cluster context of multiple machines. So these first workers will apply a mapping function, which is common to all of them, and it's going to be applied to every batch of data. Then a shuffling process will occur, which it's basically redistributing the outputs of the mapping process based on certain keys that must be provided at this step. And in the end, the output of the shufflers that have organized the mapping output based on the keys, this output will be applied with a reducing function, which will basically apply the same process to all of the batches and finally give us the final output. So at this point, this sounds very abstract, and let's see how this looks with an example. So imagine you have a large collection of files with many words on them, and you want to apply this MapReduce pipeline to count the number of occurrences of each of the words in the document. So you can start with a data batch like this one. You will split it into several batches. Then you will send to these batches to the workers, and you will apply a mapping process to all of them. So in this case, the mapping could be just generating a vector of pairs, where each pair is going to be the word itself and a number 1. Then the shuffling process will combine all the same keys together into a single node, and this node will be transferred to the reducers, where the counting of the number of occurrences for each word is going to be occurring. In the end, the final result will be prompt as a single node. So I'm going to recap a little bit on the syntax of our RuleDSL. So let's first focus on how to define the rules. So we are going to be using this add_rules macro, where we provide this namespace, which is particularly good for organizing our rules and avoiding name clashing among them. Then we define the rule name, we define the rule arguments that it can take, and we can define now the body of the rule. So here we can add some additional code to make transformation, for example, to the rule arguments or whatever you need. And in the end, you must provide an atom. So you provide the atom name here, the attributes that this atom accepts, which are basically the attributes of the structure behind the atom. And then you must provide the dependent nodes here between parentheses, which are basically nodes based on other rules. Okay. So the atom itself is going to be the responsible for processing all the data that is given here on the dependent nodes. Okay, so the idea here on this talk is to build a rule like this one we have here, which we will call MapReduce, and it's going to accept the batches of data we will provide. Then it's going to accept a generic mapper, and then a shuffler as well, and a generic reducer. Well, we will see how to make the definition of this rule. So here it's important to mention that this rule that we are going to build, all the dependencies, all the arguments here are of type rule DSL node ref. So it's important to mention at this point what it's a node ref. So it's basically a data structure that refers to another node in the graph. Okay, so we need to mention that every node in the graph is created by a specific rule. So the dependency here on another node can be understood as the dependency on the underlying rule. So a rule like with a node ref parameter or many of them is called a high order rule because it defines a generic pattern whose behavior it's going to depend on the other rules, yeah, that you will be defining here. So this is extremely powerful in order to define abstract and high level logic and behaviors. And this is, for example, what we want to do at this MapReduce pipeline. So we can also pass a high order rule as a parameter to another rule, and this can lead to creating even more higher order rules. So it can be as abstract as you want. So this ability to nest high order rules is one of the reasons why the RuleDSL is both low code, which is one of the parts of Stellar, and it's expressive, and this is one of the biggest benefits of graph computing. Okay, so let me now jump after this introduction to our tutorials site that you can also access. And we will be working on this MapReduce tutorial, which is number 3. And in the end, I will also show a little bit the fourth tutorial, which is on distributed machine learning, which is basically reusing this pipeline. Okay, so you can still go through this introduction yourself, and it's basically explaining what I've been showing before. We'll start from the generic MapReduce here. Let me enlarge it. I think the size of the screen it's okay. So let me know if it is too small. I will enlarge it. So the first thing we need to do here is to start defining the mapping process. And we will start guiding ourselves through this word count example. So imagine you have a sentence like Mary has a lamp. And the mapping process for this particular problem will be transforming this into a vector of pairs like this one we have here. Okay. So along this talk, we will be using this apply function atom, which is a really handy atom that can accept a particular function and its parameters, and then apply this function to any kind of data that is related to this. So this apply function atom is defined on data science package that is on Julius. So you can use it whenever you want. So the idea now is first we are going to load our libraries, and we will define the word map function that is basically transforming the sentence into a vector of pairs like we've said before. And the rule here for the mapper is going to accept a data batch that is going to be a node ref and a mapping function which in this case, for the word count example, is this word map function here. So you see, we use the apply function atom. We provide the map function as an attribute for it, and then the data node ref is provided here as a dynamic dependency. So by doing this, we can imagine you already have defined the several batches here, and we'll see how we can define that. So for each batch there, you can create a node ref based on this mapper rule we have just defined, provide this batch as an argument, and then the mapping function, which in this case is word count. And then we can define another rule, which is map reduce, which can take all the batches, all the mappers, all the shufflers, and reducer. So this could be an approach for this problem, but it's actually problematic because it's putting much burden to ensure the consistency, because we have to define all the mappers, all the shufflers, and reducers, and each of them are based on the previous one. So it's gonna be easier to build it in another way, and we will see how we can do that. So the mapper, it can be defined without passing the first argument. And that is because we can use this prepend function that is defined here, that allows us to put the first argument, that in this case is the batch of data, later on when doing the MapReduce rule definition. Okay, so this idea of avoiding passing the first argument to the mapper, shuffler, and reducer will be used along this tutorial, and the data batches will be provided at the MapReduce stage. Okay, so let's now define our batching rule. So this batch rule will be accepting, for example, a sentence, and then we will use the apply function atom again. The function that we will apply to this is just the identity. So this is basically transforming a sentence into a node ref. So it will accept the sentence here as an attribute because it's not a node ref yet. And so here we will start, for example, defining the our data source, which are a couple of sentences. Then we define our batches from all the sentences, and then we can define this mapper node based on the mapper rule, but you may see that we are avoiding passing the first argument. So to note that, we are using this underscore notation, which basically means that we are not passing the first argument to them. So we can now use the prepend function to illustrate how we can use it to pass the first argument to our mapper. So we can create a vector of no ref by using the mapper rule, using the prepend function to give this input for each batch. So we can run all this, and here this particular code is just for transforming the node labeling, which is really good to have a better understanding on the graph. So I will not enter into the details of how this is written, but you can take a look, and it's really handy to do this. So here the node has been built for this pretty simple task. And you can take a look on the Jupyter notebook, or you can go to the web UI as well. Yeah, I will run again all this because after 15 minutes it's going down. So I will restart the kernel and run all the cells. Sorry for this. Yeah, so now we can see it. So it's a pretty simple graph where we have defined the 3 batches, and then the mapper have been applied to each of these batches. So you can also see the information here, and it's pretty simple. Okay, so after the mapping process, we have to define the shuffling process and then the mapping process as well. So I will not now enter into the details as we have done with a mapper, but I will mention briefly how this is built. So the first thing is that the shuffler needs to take the output from the mappers and split them into multiple chunks by certain key values that have been computed in the map data. So in our mapping process, we've said that for the word count example, the keys are the word themselves. Okay, so we have to shuffle and combine all the same words together into single chunks that they then can be grabbed by the reducer. So we have to move these chunks around that so all the data with the same key is gathered together, and we have to concatenate all the chunks at the gathering node to recover the full collection of data. So we need to define this split by key function, which we have to provide here, which is the key function we are using. So which is the function that applied to the mapper will extract the keys. So we'll see in our case it's pretty simple. And by using this function, we can define a split by key rule, which is based on this function. Then we can define a select key node and a merge by key node. So these three nodes are pretty simple and are going to be used here on the shuffler. So all these three rules defined previously are used here, and they basically are doing exactly the same process that we have described here on top. Okay, so you can later take a look into this. It's not complex. It's pretty similar to the mapper. So now we can define our shuffler node based on this rule, and we will provide the mappers. So this is the input for them. This is the function we are going to use to extract the keys from the mappers. So the first function is taking the first value on a pair, and remember we had vector of pairs where the first argument was a word. And here, this is a limitation at this point. We have to provide all the keys that can appear on our dataset. And why is the limitation? Because we can know beforehand which are the several keys that may appear in our dataset. So bear this in mind. In the end of this part, we will see how to deal with this, and we will completely solve it. So now, just to make it easier, we can see this graph in our web UI and see which are the additional transformations and nodes we have added. So the previous step was finishing here on the mapper, and now we are adding this shuffling process, which are these 4 stages here. So the first one is splitting the mappers by keys. Then we are selecting by keys and combining all the results together. So you can see words are grouped together here, and then they are returned as a final result. But the reducers that we are going to define now will start from this one here. Okay, so bear this in mind. This node will disappear in our in the following graph I will show. So the reducing step is pretty similar to the mapper. We are going to define a reducer rule, which will take the output of the shuffler and will accept a reducing function, which in this case, for the word count example, is nothing but counting the number of occurrences of the word on the shuffler. Okay, so we use the same apply function atom, and we provide the shuffle as a dynamic dependency again. So for the word count example, here we define the reducing function. It's a really simple function. And now we are able to define our map reduce finally. So this rule will accept the several batches we can define based on the batch rule we defined previously. Then it will accept the mapper, shuffler, and reducer in the way we define with an underscore. Okay, so avoiding passing the first argument. So inside the rule, we will use the prepend function to pass the first argument to it. Then we will use it again to pass the mappers to the shufflers, and then we are going to use the same prepend function to pass all the shufflers to the reducers. And then we will combine all the results into a single node by using the merge function. So now we can define with an underscore the shuffler, mapper, and reducer. So here you may see there's no data being passed, but the first function and the keys for the shuffler, the word map function for the mapper, and word reduced to the reducer. So this definition is pretty simple. Then we define the map reduce node, and here we pass the batches, the mapper, shuffler, and reducer, as we mentioned before. So we can now create the graph and run it, and we can see it on the web UI. Okay, so we mentioned here it's a mapping process. This is a shuffling process up to this point, and now we are applying a reducing operation to each of these batches, and we finally get the final node here. Okay, so these reducers are just counting the number of occurrences and returning it as a pair. So as I mentioned before, the limitation regarding the shuffler was that we needed to provide all the possible keys in our dataset, and that is impossible in a real application. So the way of solving this is by using the hash and remainder functions. So we mentioned that we needed to provide a function to extract the keys from the mappers. We were using the first function, and this first function can be then hashed, and the output of this hash can be used to apply this remainder function with a particular number that will give us the number of shufflers we are going to use. And why is that? Because while applying this remainder function, the possible values that we will have are the collections here from 0 to 2. So if you apply the remainder function with 3, so the possible values are 0, 1, or 2. Okay, so imagine you have a value n, then the possible values are from 0 to n minus 1. Okay, so this is how we can solve this problem, because we still use this first function, but by using the hash and remainder function together, we know which are the possible keys that are going to be used. So let's now take a look on how this graph looks like. And you may see now the difference is that previously we were selecting by the words themselves, but now we are using the select, we are selecting by these integers, okay? So as I mentioned before, the number of shufflers now are 3, because that's the argument we have used for the remainder function. So this can be later on passed as a parameter. So here you can see, for example, that this node, that 2 words are going to the same node. So the reducer function needs to deal with these 2 values in the same node properly. Okay, and you may see this reducer function is well defined, and the map reduce node has the correct answer as in the previous example. Okay. Okay, so now we can redefine our split by key rule here, and we can redefine it by using our hash and remainder functions. And you may see that here the argument n is provided, so you can select the number of shufflers you can use. Okay, so any questions up to this point? Okay, so I will now show you how to apply this same MapReduce pipeline to solve another problem. And another interesting problem is the finding friends problem. So imagine you have a social network where you want to know which are the common friends between 2 specific users. So you may have this information here. So imagine you have users A to E, and you have this information for each of them. So you have, for A, you know that the friends are B, C, D, and for B, you know that the friends are A, C, D, and E. So if you want to find the friends in common for each of them, you may see that if you only count with the information of A, you can say that the friends in common between A and B may be C and D. And if you see the information from B, you can say that the friends in common are C, D, and E. Okay, these are the possible values for each of them. So the mapper, to solve this problem, needs to take into account which are the possible values for each of the friends, based on the information on the users. Okay, and then so this is defined here on the mapping function. Yeah, you can then take a look on how this is built. And the reducing function is basically computing the intersection of these sets, of these subsets. So you may see that the correct answer to find the friends in common between A and B is the intersection between the subset CD and CDE. Okay. So you can use these functions to define your mapper and reducer. Then the shuffler will use the first function as well, um, and we can run this whole graph and see the output. Okay. So okay, so now you can see the graph. I will go into some details to highlight how this works. So you can see that in the mapping process, for each of the friends that for each of the users, sorry, that are the several batches, you apply a mapper and you compute which are the possible friends in common that a friend and these users may have. Okay, so you compute that for all of them. Then you split by keys and you combine all together here on the shuffling process, and you apply the reducer to take the intersection of these outputs. And then you combine all the results together in a single node, and you may see here for A and B that the result is correct. The friends in common are C and D. Okay, so let's go back. So here it's another example. It's a group by example. I will not show it now because I prefer to save some time to show you the distributed machine learning pipeline briefly. But you can take a look. It's basically the same logic applied. You have to define a mapping function and a reducing function, and then you can solve the problem. So the good thing about this pipeline is that the user only needs to think about which is the mapping and which is the reducing process that they need to apply to solve the particular problem they are dealing with. Okay, so yeah, you may see here it's a graph. Okay, so now before showing how we can make the distribution of the previous pipeline, let me talk about some advantages of Julius graph. So in particular, I want to make some comparisons against function composition, because you may find some similarities between high order rules in our RuleDSL with functions with high order functions in languages like Haskell, for example. So the first things I want to mention is that while using high order rules, this doesn't create typical stacks, and the result is nothing but another graph. Okay, so this ensures that to the developer to visualize and debug to be a really easy process, while if you are using a function composition, you need to use a debugger to access the intermediate results and call sequences, and this is a much complex process to do. So another thing is that the resulting graph composition can be automatically distributed without any code change, and you will see that this is really easy just in a few minutes. If you want to do the same with traditional functional code, this is not really easy make it automatically or efficiently at the same time. Then the graph composition is much more flexible. So once you build the graph, you can run it in different modes, like Yadon explained before. So you can use both batch and streaming modes to basically the same case without many code modifications. And this is basically impossible to do in this way with traditional functional programming. And the last thing is that while graph compositions can mimic function composition, the reverse is not true. And the MapReduce is a good example of this. So let's now focus how to make the distribution of our MapReduce pipeline. We will see how easy it is to do this. So the first things we need to do is to define some configurations on top, but we'll not enter into the details of this. It's basically the same for any project you are dealing with. So you just have to repeat this code. And here we start our local master service, and here we define the number of workers that we are going to use. So this can be done basically on two ways. We can use a cluster with many editors, or like in this case I'm showing, we can mimic the cluster behavior by using the several cores available on our computer. Okay, so in this case I'm going to use 3 cores available on the CPU I'm using. The code for any of these cases is basically the same. At this URL, we are going to see the outputs. This is a web UI, and the first thing is to import the modules you are going to use. So the difference here is that you need to use this macro, remote deval, and you have to provide this connection to the graph. Okay, so this is a remote graph proxy object defined here. You have to provide it in order to make the connection, but the code is going to be the same. Then to add rules, you need to provide this add rules macro as we used previously, but the difference is that you don't only need to provide the namespace, but the connection to the remote proxies also you need to provide it. So after this, you can make the rule definitions like we did before, and you may see that this is an exact copy of the code above. Yeah, so any modification have been done. And then for any arbitrary code like functions or structure you may need to define, like the prepend function, the split by key, where reduce, whatever, the node labeling display. So any function can be defined by using this remote eval macro. So this is basically making the connection with the workers. So now we can use this, provide the same data source as before, create the several batches, define the number of shufflers we want to use. Here is the parameter n passed, and we can now run the computation. But an interesting thing here is that because we are doing distribution, we can let the user to say which are the nodes that he wants the distribution task to base on. Okay, so the most efficient way to distribute this, you will see it immediately in the graph, is that you can base the distribution on split by key nodes and the reducer nodes. So this is going to be distributing the task among workers efficiently. After doing this, you can dispatch all the job by using this function, and the computation will be run. Again, you can see this display here, or you can go to the web UI that was on this URL. Okay, so now you can see that this is basically the first problem, the word count problem I showed you, and the one we have used to build the MapReduce pipeline. And here you can see that different colors appear. So what does this mean? Is that each color is a different worker. So you can see that because we specified split by key to make the distribution on this, the 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 graph have been distributed among the several workers efficiently, and also the reducer have been specified at this stage, and also the task is efficiently distributed. But of course, during the shuffling process, there's some shipment of data across, and you can't avoid that, and it's okay. Okay, so this is pretty all from the MapReduce pipeline, and you can see that we have built a generic MapReduce pipeline from scratch just by using 10 rules in our RuleDSL and 20 additional lines of code for defining some functions. So here the results speak themselves. We have done it in a single core process, but then we could easily distribute it among several workers just without any code transformation. So this is one of the biggest benefits of using our RuleDSL. And the last thing I wanted to show is our next tutorial, which is called Distributed Machine Learning. And this, I will not show all this code. I will simply show you how this is built. So here we define a simple machine learning pipeline like Milena did in our previous example. We also define how to do some downsampling. Sorry, I forget to mention that this tutorial is based on this popular blog post that is called Training Models When Data Doesn't Fit in Memory, which is describing how to use Dask to create a bagging pipeline for machine learning. So here we show how to build the machine learning pipeline with bagging, still without distribution. And here in the end, we show how to use our RuleDSL to distribute this machine learning pipeline. But the good thing about this is that we are reusing the MapReduce pipeline, where the mapper, in this case, is nothing but machine learning, training, and validation. And the reducing stage is combining all these multiple models into a more powerful and robust model, which is basically bagging all of them. And you can also see on this tutorial that we are both using batch and streaming mode. And here it's the streaming in the end. And if we refer to this to the web UI now, you may see that the streaming output is displayed. So here you can see on this tutorial that all the mapper is this process here, which is training and validation several models in a streaming way. And here all the validations are combined, and the MapReduce is basically providing the final output. So you may see on this last node that several records of the score are computed. And here you can see that the score is getting better as you start bagging more and more trained models. Okay, so this is pretty all from my side. Of course, I'm more than happy to answer all the questions that may arise at this stage or later. So thank you, all of you, to your attention.